Slideshow should work. I never use this. Okay, so I'm going to try to tell you a little bit about implicit programming, which is a research direction that has somehow crystallized in the last really 2 years, or even less, in our research group. And really, it's an attempt to address the questions of software reliability. And you could address it by verification, or you could address it by trying to synthesize more of software functionality by construction. And this comes to the notion such as automatic programming, which is a term that is not very popular today. Perhaps today people would talk more about synthesis. And I put up this very old paper. In fact, it's from 1958. And at that time, automatic programming meant Fortran, right? And the Fortran stands for formula translation or formula translator. And at that time, that meant that you would get already some notion of automatic programming by translating expressions into sequences of assembly instructions. So now it's a few decades later, right? So we could ask the question, what would automatic programming mean today? And if you think about various activities that developers are involved with, you could talk about having some source of requirements and then interactively developing a piece of code in some integrated development environment or some editor, well, let's say Eclipse or Visual Studio or Emacs or VI. Then you would compile your program and you would get some sequence of instructions, and in the end you would run the program on some machine. You would get the answer. And as already Douglas Adams pointed out, you need to reformulate your requirements from time to time to see whether you're solving the right problem. So I would like to suggest that we look at these different stages of development and see, is there a way to leverage the increased computing power that we have at our desktops in many of the devices that we are using. And we want to leverage this additional compute power in order to increase programmer productivity. So what I'm going to be showing today is not going to really help you create faster code, but the idea is to really make it substantially easier to develop code, and especially if you do not have experience in developing some algorithms for difficult combinatorial problems. And so this is also the agenda of today's talk, right? So I'm going to talk about the improving or making more flexible the execution platform, the compilation process, and also the development within integrated development environments. And so my claim is that automated reasoning, and I'll tell you in a second what I mean by that, can play a key role in all of these aspects of the development. So let's look at an example. So this example comes from real code. It's a very small piece of code, and it's written in C, I believe. But for the purpose of this talk, you could imagine it's also Fortran, so 1958 technology. But of course, these are the kinds of programs that we are used to looking at. So what this program tries to do is actually knowing a total number of days, which is a convenient way of specifying rough approximation of time, find out actually the year in which we are and the day in this year. Okay? And so this is the code. So perhaps you can take a look at it just for a moment. So we start from, we are given the total number of days, which are supposed to be interpreted as days since 1980, and then as long as we have more days than one full year, we subtract this, right? And we also need to check whether we have a leap year, as you know. And this is leap year. You can assume this is a correctly written function that checks whether current year is leap year. Okay? So does this look fine to you?
What does it return?
Oh, it returns in the end, I didn't really put everything, but it returns these leftover days and the year. Okay, so you get back year and day. So, for example, you get 2011 and 181st day.
It's a Boolean.
Well, okay, so in this case, it would set this somewhere and then do something else. I apologize for the, okay?
It's Fortran, it's global variables all over.
Yes. So this actually likely is actually that there's some global variables involved. So this was actually a part of a music player, a boot sequence, and a music player of a relatively popular brand. And so on December 31st of 2008, all of music players froze when you turned them on. Okay. Can anyone see why?
Well, I actually know the example, so I know they should be greater or equal, not greater.
Yeah, so if you don't put greater than equal for 366, then you enter an infinite loop when number of days is equal to 366. Because if it's not strictly greater, but it's equal, then nothing happens and you just loop forever. Okay, so this is an example of a real bug, and I have picked it partly because it's a problem that can be naturally reformulated using a particular programming style that I'm going to suggest. And so using implicit programming, you would specify what you want to do by writing down a constraint. So in this case, you would define simply the origin year as before. You would define something like number of leap years until a given year. And then what you would have here, let me see if this works, you would basically say that you want to find year and day, just like before you wanted to find year and day, such that this constraint here holds. Okay? And so what does this constraint say? So this total number of days that you had is given by, well, multiplying the number of days in a year, and then you would add what you get from leap years, and then the leftover day that you need to return also needs to be added up, right? And so this is somehow a nice mathematical expression that you can reason about, and you can reason end-to-end about the behavior of this program. So there's no loop involved in particular. And of course, if you want to have to narrow down the solution that you want, you also need to specify the constraint on the day. In this case, we want day to go from 1 to 366. Okay, and you can read this in English by saying, knowing the number of days since 1980, find the current year and day, and you say find the current year, find year and day such that this constraint holds. Okay, and so this is the first main idea of implicit programming. And so basically we didn't write how we want to compute year and day. We wrote the relationship that they should satisfy, or the constraint that they should satisfy. And in that sense, this is one of the primary meanings of implicit programming, that we are programming with constraints. And note that we can still write equations that define values like before, but we also can write these implicit constraints that are not based just on explicitly defining values. So we have more freedom. And also, often we can write code in a way that does not involve loop, for example, and we can more easily reason about the termination of such programs. Okay, so basically there are now two ways, if you try to work with the solving implicit constraints, that you can run them. Okay, because the key challenge is now how to make this executable and ideally efficient. So one way is to wait until runtime, so that you have the concrete value of days. This is some parameter that we always knew. You know this value, let's say 5,000, and then you find a year and leftover day such that this constraint holds. Okay, so this would be invoking a constraint solver at runtime every time. Wait, there's a question. Yes.
Yeah, if I may ask. I mean, I'm wondering about the correctness of this. Couldn't this give me a year that is too small and a day that is 366, for example, or 365? I mean, the day value can be very large, and couldn't it be that? You mean
is 366 too large? So it could be that this constraint actually has multiple solutions, right? But in this particular case, if you inline this, you will get the constraint in a decidable logic, and we'll be able to answer questions like this. For example, one question that you would like to answer is, are there multiple solutions? Right? Is the solution unique? Can you obtain a value such that the year is actually is not a leap year if you define leap year in yet another way. Okay, so the point is that partly because we got rid of the loop, and partly because we are stating the properties that we care about, we can reason about this code more easily. And I'm not even making particular claims about this piece of code. Perhaps it's not ideal of formalization of this problem of finding the day and year.
What happens if you have multiple solutions,
You will get a warning, and you can decide to refine, or you can, for example, search for a least solution and so on. So I'll have an example later on. Okay. Now, but in order to do some of the analysis, you actually would typically try to compile the constraints as well. And this is the second way of addressing this problem. So here, I'm not going to know actually what the number of days is. Okay, so number of days is just going to remain as some parameter. And in that case, I would like to generate a code which is a function of these parameters. Okay, so this, sometimes I will have 5,000, sometimes I will like 6,000, or any number, but I would like to get a function that will produce always a correct notion of correct a year and a day as a function of this parameter. Okay. So we have explored both of these alternatives, and I'm going to talk about the first one first, and then the compilation approach afterwards, and then I'll continue with another aspect of implicit programming. Now, in any case, the key technology here is automated reasoning. So one manifestation of automated reasoning is theorem proving, where we often deal with semi-decidable problems. So we have a way to enumerate solutions, but not necessarily a way to terminate. And typical instances are finding a proof that the formula is valid, or dually that its negation is unsatisfiable. And if that's not the case, then we would like to hope to find a counterexample, or in other words, when negation of the formula does have a satisfying assignment. And now, that's the theorem proving problem, and unfortunately, it can be somewhat unpredictable. A more predictable situation is when we have a decision procedure. So when we identify the fragment, for example, integer linear arithmetic or its combination with some other languages, where this theorem proving process in some sense always terminates. And typically we then don't use a general purpose theorem proving process, but a set of specialized techniques. So in that case, we will always either know that there exists a proof or there exists a counterexample. And typically, we will be able to compute when the counterexample exists. We will be able to actually find those values. And here, in general, for different class of formulas, or you can think of this as different class of programming language expressions, we get a different technique, different decision procedure. Something that's also going to be related to this talk are quantifier elimination procedures, because they will be able to solve these parametric problems where you have some number of parameters. And now, some of these ideas of constraint programming and constraint logic programming have been around for a while, but there's something that changed in the last decade. And this has been actually progress in practical implementations of set solvers. So, for example, techniques such as a particular form of backtracking, efficient propagation, and learning have been incorporating into set solvers, and they have led to dramatic improvements in the performance of these solvers on examples that come, for example, from hardware verification or software verification. And of course, I'm not saying that the NP hardness is not there anymore, but there's an empirical observation for the kind of problems that we often produce, that we now have much better set solving tools. And another thing that happened even more recently was the development of satisfiability modulo theory solvers, or for short SMT solvers. And those of you who have attended the talk of Nikolai Björnet know what I mean by that. But basically, the key idea is to combine the best of set solvers. So there is a set solver inside every SMT solver, and the implementations of some of the most important decision procedures that are relevant for program verification or hardware verification. And this I wrote here as a simple equation, but it's actually a non-trivial process, both theoretically, because you want to guarantee that you still get a decision procedure for the entire class of expressions. So you always terminate with either a proof or a counterexample. And practically because you want to deliver efficient implementations that work well in practice. And there are competitions of SMT solvers, and there's continued progress in this field. So now we would like to leverage these advances in being able to execute declarative constraints. So let me tell you through a few examples what we could do.
So just before you go into I was wondering, it's more a philosophical question. So constraint-based reasoning works well for a certain set of problems, and in some sense, I mean, programs are formulas, and it's kind of like energy and mass. You can convert back and forth between them, but it's kind of more convenient to be in one form than the other. So I'm wondering if you think back to the example that you gave us earlier with computing the dates, do you think for programmers it is easier to reason in terms of the sort of declarative way of specifying how to compute this, the formulas, which has the advantage of, say, having no roots? Or is it easier to think in terms of this sort of the imperative algorithm of, okay, here's how you go about computing it? I mean, in computation, I guess there are problems and problems. So what do you think about the whole problem?
I think this is an excellent question, George. And actually, partly because of what you are saying, we are not suggesting to eliminate imperative and functional programming as we have it today. So the system that we have allows you to use existing techniques, but it gives you an option to use also constraint-based programming. And I think this option is important, especially if you think about not just writing some program, but writing a program and making sure that it does what you want it to do. Okay? And partly it's because of the simple fact that you can formulate precisely what is it that you want the program to do. And often you can then use this formulation, the most natural way of describing what you want to get in order to get the first result. And so I'm not saying that every program is more conveniently formulated in this or the other way, but I think that overall it helps you. Okay.
Just a short question. Do you have some metric to compare two programs that are both correct? Which one is better?
Two programs that are both correct. One simple metric is the length, and the other metric is being able to prove something about this program. For example, prove that it terminates or prove that it doesn't crash.
Think about long computational tasks that you cannot afford so much time to run it for. Sometimes they run forever. Like think of search, think of algorithm for
Okay.
So they are correct, but you need to come up with an algorithm that is efficient enough.
You know they're correct?
So, for instance, I'm using your tool, so I just realized that they are both correct.
Both meaning?
So I'm comparing two solutions.
Okay.
So and I want to come up with a solution that's more efficient.
I see. So you mean whether I can automatically somehow measure these things for performance? Yeah, so we didn't look so much at the performance, but termination, for example, would be easier to check. On the other hand, actually, there's some ongoing work with Christoph and Andre, where we are looking at declarative descriptions of problems, and precisely because we expect that it will be easier to quantify some performance properties like memory usage and running time. So I think declarative descriptions would typically help you. And there's another aspect here, not just being declarative, that's closely related, which is being domain specific, because you will see that these. This is also related for the developments in Scala on domain-specific languages, that we have particular solvers for particular domains, and that's why we can solve these constraints, and that's also why we can analyze them. Okay, so perhaps we'll see some more examples of what this looks like. So one way to do this, as I mentioned, is to solve these constraints at runtime. Okay, so let's look at this first because it's conceptually the most flexible way, and we have the implementation that perhaps accepts the most varied class of declarative constraints here. So the idea here is that you run your code. Let's say we have actually implemented these systems as extensions of the Scala programming language. So they run on the Java virtual machine. But then you have these implicit constraints. So what is happening in this approach, these implicit constraints are shipped into a constraint solver. In our case, we have our own implementation of a particular constraint solving algorithm that underneath uses the SMT solver, about this technology that's based on SAT and on decision procedures that I mentioned. And then you get back the answers to your constraints, and then you continue to compute with them as values. So this is conceptually a simple thing, but it hasn't been implemented with this degree of efficiency and with these state-of-the-art SMT solvers before. So here's some of the things that you can do. If you want to do SAT solvers, well, that's a trivial thing to do because you have a SAT solver as part of your language. So one common format is conjunctive normal form, and so which looks like this, right? So this is just a conjunctive normal form formula. And if you represent it as a sequence of sequences of integers, where integers just denote these indices, and if it's a negative index, that just means it's negated literal, then here's a piece of Scala code that builds a constraint. And this just shows that functional programming is great at building the constraint. But then what our system allows you to do is to just say, to solve this constraint, and this solution process happens in the efficient SMT engine of the underlying solver. Okay? So you can write trivially a SAT solver, and it will be solved efficiently. So and this combines the advantages of functional programming for describing the problems and with the sort of SMT solving for solving these problems. But it's a very simple example. Okay, so but now you can also look at, for example, knapsack problem. And here I'm just showing it to see that you can describe it in a couple of lines of Scala to generate the constraint. And here's what you can just invoke and get the list of these two vectors that are involved in a knapsack problem, and then you can solve the knapsack problem and generate. You obtain a solution, which is just again a value in Scala. Okay, so this is pretty transparent to the user, and you're simply you have now capabilities of constraint programming within Scala, supported by a relatively efficient engine. So this one here, you can see that we can also maximize the values, and this is a functionality that we have implemented on top of the solver that can just check whether there exists a value or not by using a kind of search. But there may be more efficient ways to do it in some other constraint programming community problems. So let's now move beyond some numerical examples and look at sorting of a list. This is a classical, perhaps, logic programming example. Unfortunately, there are many logic programming systems where this will not work, or examples like this will not work, especially if you want to, let's say, ask, find me a sorted list and check whether there exists any additional solutions to this finding a sorting list example. Okay, so sometimes you'll get first solution, but upon asking to find another one, some prologue-like, for example, execution mechanism can easily run into an infinite loop. So here we have a little stronger guarantees on when we will succeed to find solutions and to enumerate solutions. So this is just basically a Scala description of a list and description of a set of elements in this list, description of the predicate, what it means to be sorted, and then you say, find me a list that is sorted and, for example, that has the equal, has this particular content. Or you could say that it has content equal to the content of another list. Okay, so this also just illustrates how easy it is to describe something like this. And let me now move to one more complicated example, unless you have questions about the sorting. So one more complicated example would be red-black trees. And so red-black trees are, of course, familiar to most of us. They're described in some common textbooks. And this is a textbook by Korman, Rivest, and Leiserson. And so you can see that there's around 30 pages overall dedicated to this description. It's a very nice textbook. And it comes after general search trees. So you will see that, for example, you can describe red-black trees using 5 properties, 5 invariants of this data structure. And then, right, you have 29 remaining pages saying how you implement these things. So the question is there a simple way, even if I'm willing to suffer some performance penalty? So one thing that I think is very important is to be able to document what a red-black tree is. And so here's how you would do it. You would just write a piece of Scala code that checks whether a given algebraic data type is in fact red-black tree. So this is definition of algebraic data type in Scala, these 3 lines. And then you would check, for example, that it has equal black height on all paths. This is what these 2 functions do. And you would check also that red and black colors alternate, and that you would check that the tree is also sorted. All of these are simple recursive functions. Okay, so now, in order to express some operations, it's useful to talk about the content of a tree. And here I define content as a function that maps a tree into a set of elements, just sort of like this. Again, simple recursive function. It's sort of important that it's a treefold that's defined by this simple recursive schema. It's important for predictability of our techniques. Then you can define insertion like this. Okay, so this is insertion into a red-black tree. So I'm searching for another tree that is a red-black tree and whose content is equal to the content of the original tree extended with a given element. Okay, so this runs. It doesn't run particularly fast, but it runs. So now, to illustrate really what's the added benefit here is that suppose we had the red-black tree implementation, and sometimes you actually don't need removal from red-black tree. So you implement only insertion and lookup. So let's say we want to add remove, right? So this is code for remove. It's around 140 lines of C code. I took it from the website of actually Emin Martinian from MIT. And what you need to add in our case, once you have written all the invariants, you just need to write again these 2 lines. Okay, so the point is that the biggest payoff comes from reusing this declarative knowledge because, for example, invariants are common for all the operations that you do.
How long is the code in Scala for deletion? I mean, if you have got pattern matching and all the things.
I would have to estimate. Does anyone know the Scala collection library implementation?
It's a red-black tree.
Red-black.
But it's also long.
So I would estimate several tens of lines. Okay. Because you need to rebalance it. But it's true. I mean, so part of the savings come from using functional trees, but there are added advantages from using declarative programming. And in fact, you can write explicitly implementation of red-black trees in Scala, so purely functional programming, no constraint solving, and then you can write these invariants and check that they're satisfied. And essentially the same techniques that we use can be used to show that. And so we can show most of the invariants completely automatically. So there's another question.
Why would you actually want to use red-black trees? What is their advantage over other data structures? Like, isn't it the performance that you want?
That's right. That's a good point. Red-black trees are not an ideal example. A better example here would be, let's say you're building some compiler syntax tree and you want to ensure certain properties, right? So something that's a more user-defined structure rather than a library algebraic data type. Okay. Sorry.
Now, if you would ask me to write remove with maximal reuse, I would simply start with an empty tree and insert all elements except the one that I have to remove, right? Mm-hmm. It would be like 3 lines. Would this approach that you're proposing be faster, or does it internally something similar?
It could be as slow currently, but you have a point. This would be one execution mechanism. The question is whether you would know that, for example, all the invariants would be maintained. So I think this is an interesting way to approach this problem as well. But there are certain cases when that wouldn't really help you, right? If you take the time example. Yes? Well,
it's my understanding, although it's been a while, I choose not to teach red-black trees, I teach ADLT. But it's my understanding that those 5 invariants imply that the tree is balanced, there's a balance condition, and that only implies that you can do lookup in all log n. invariants by themselves will not tell you anything about how to maintain them. In other words, you insert the function, the actual cleverness of doing a certain remove in O of log m is nowhere in those invariants. It's in the other 29 pages.
That's right.
Is that right? I just
yes.
want us to be on the same.
Yes, I agree. I think you have the point.
But and your implicit definition of insert and remove, that still doesn't even guarantee that they will actually run in log n time, although
that's right.
They should, because the tree is balanced.
That's true. So one of the questions here, and that's why I'm making a risk here by talking about a fresh research agenda, is how do you make this efficient enough, right? I'm going to actually skip some ability to enumerate trees, which you can use for testing, and then, well, I would like to come back to this point, but one technique that I would like to use is compilation, okay? And I'll tell you how we can compile certain numerical constraints. And extensions of these techniques, I believe, can be used in order to create code that does have closer to the expected running times as well. So let me just go back to say how this and when you would expect this to work. So this is based partly on decidability results that say that if you have a decidable logic, you can actually extend it with recursive certain classes of recursive functions. And there's a very interesting property of these recursive functions that you would like to have, and this is that you have multiple values that map to the same one. So it's somehow opposite of injective function. You, for example, if you have a tree, there are multiple trees that denote the same content. Okay, or there are multiple unsorted lists that denote the same set, that store the same set of elements. And if you have a function with this property, then it turns out that you can get a decision procedure if you had a decision procedure before. So it's a general way to extend the class of constraints that you can solve. And so we have used that, then this theoretical result that we proved in POPL 2010 to implement a verifier for programs. And there we basically use this to detect that functional programs are correct, or that functional programs have a counterexample. And turns out that so this is work with Philip Suter and with help of Alison and Quixel. And the idea is that whenever you have a counterexample, this will find it. Okay, so this is basically like a dual to the situation you have in first-order logic theorem proving, because you are solving a semi-decidable problem, yet you are complete for counterexamples as opposed to proofs. And turns out that this technique is actually complete for this class that we have established before, and you can play with this verifier for functional programs at this link. And then, so what I'm proposing now, basically, and we have a system that shows that this can have a lot of interesting examples where it applies. You can actually use this as a computation mechanism, because these counterexamples can simply become the values that you want to obtain and that satisfy the constraint. Okay, and so we are releasing the tool soon, but the paper is already up, that you can read it from our homepage. Okay, so that's the idea of running these constraints at runtime, and as you correctly pointed out, there are big questions about performance of this code, but I think it's a great way to experiment. Now, we would like to compile these constraints and to make them more efficient, and I'm going to show you some techniques that you could use for that. So we have done this primarily for arithmetic. And so here's a related example to this day and year computation. So you have the total number of seconds this time, and you want to split it in hours, minutes, and leftover seconds that satisfy some constraints. It's actually quite similar to the previous one. It's just a little bit simpler, perhaps. And so what you would like to get is some code that computes these values. And now you know immediately how you would do it, right? So but this is the code that gets generated. Actually, I'll show you the code at the end. I'll first tell you how we proceed in starting from an arbitrary constraint in this class, and always guaranteeing that we will produce some code, and the code will produce the values that satisfy these constraints. Okay, so this is the construct that we will use. We can say choose a value that satisfies a constraint, and we have in fact implemented it like that in Scala. So there's a higher order function choose that then our compiler plugin intercepts and then transforms this into more efficient, hopefully more efficient code. And this is related to the problem of quantifier elimination, because here I'm asking, find me a value x that satisfies a constraint, and quantifier elimination says, suppose that we want to check that there exists a value that satisfies a constraint. What is this equivalent to? And there's a very important difference, which is quantifier elimination throws away exactly what we need, right? We need actually a value for this x. But what is interesting is that this value may depend on the other variables in the formula. And this is why quantifier elimination is solving a parametric problem. And we'll see examples of that in a moment. So the basic idea is that instead of just replacing, let's say, there exists x such that s of xa holds with some p of a, this is what quantifier elimination does. We would like to replace this thing with a specific value for x. Okay? And turns out you can do that for most cases in practice. For example, the simplest case is one-point rule. And there you shouldn't be surprised that this can happen. So there exists x such that x is some term containing a and something else holds. This is equivalent to s of this term and a. Okay? And now this term is actually the witness for this x. And this gives you the quantifier, this gives you the code generation procedure. Okay, so if you have a constraint that has equality, or if you can reduce the constraint to one that has equality, then this code generation is simple. But turns out you can do it, so quantifier elimination procedures have been studied for many expressive logics. And in all of those cases that we have looked at, we were able to also identify the corresponding witness terms. And there are even quantifier elimination techniques based on that. So we can basically generate code using a quantifier elimination. So this is an example with equalities. I should just mention that for inequalities, if you have integer linear arithmetic, you would use something like Fourier-Motzkin elimination if you know this. Okay, so basically you look at lower bounds, upper bounds, combine every lower bound with every upper bound. And then, of course, you have to take care of divisibility. So I'm not going to go into the details, partly because I'm running out of time. But you do get some reasonable looking code in examples like this. Okay, so it's a code that involves some arithmetic operations, and perhaps it's not exactly what you would write, but it has, again, good running time in this case. And so this algorithm has all the completeness properties that you would expect from an algorithm based on quantifier elimination or a decision procedure. So I'm not going to go through all of them, but the algorithm itself terminates, the code that it generates terminates, and the values that are generated are always the values that satisfy the constraint, unless no such values exist, in which case you will detect it. And let me show you what means by detecting. What do I mean by detecting? Let's say you write this constraint in this example, and you say that number of hours is less than 24. Well, then you will get a warning that there are certain values of total number of seconds that for which the constraint has no solution, and you'll get an example. And similarly, if you relax the constraint too much, then you will get a witness showing that in some cases you have multiple solutions, right? So you can use that to decide that I'm willing to live with any of these solutions, or say I'm going to strengthen the constraint. Okay, and that actually has interesting applications to some programming language constructs. This shows how we extended the pattern matching in Scala so that you can write pattern matches that are integer arithmetic expressions. They're related to Haskell's n plus k patterns, but more expressive, in fact, if you know Haskell.
What if you do have multiple solutions?
Mm-hmm.
So
it will give you one, always the same one.
No, but you say it flags that, oh, by the way, this may be too relaxed,
right,
but there are multiple
yes,
solutions. So then let's say you have a sorting algorithm that admits different ordering, they're still consistent. There's also different ways to do that. So would you then tell, like, oh, that's okay, or you can analyze the set of possible solutions and say which should be admitted, which not?
So we can enumerate solutions in the runtime approach. In the compilation approach, we just generate one solution, and then if you are not happy with this particular solution, you strengthen your constraint. But ideally, we would like to have both capabilities in both approaches. So, there was another question?
Can you state which solution it is that you obtain with some simple property? Like, the one with smallest values, or
we can add maximizing constraints in the dynamic approach. You can maximize a given term. That's again, you can use recursive function to define what you want to maximize. Okay, just a remark that this also works for certain nonlinear arithmetic constraints, in particular when this nonlinearity is in terms of a parameter. But so this is not extremely surprising. I should just mention that we have also automata-based synthesis procedure, which is based on monadic second-order logic for those who know it. So it's based on generating automata that describe these constraints, and it has a pretty good runtime complexity of the synthesized code. Okay, and so here's just an example without going into the details of this procedure. So here's a table of some small constraints that we ran, and some of them are asking the system to produce the smallest value. So this is a little integer linear programming problem. And what is interesting is that because it's based on automata, it works with a bit representation of its inputs. So it will generate the program that you can accept, for example, 4,000 bits, and it will give you a solution to this constraint for that parameter, right? So we are basically plugging in numbers that are on the order of 2 to 4,000, and we are getting in the so this is, I think, 3 point something seconds. We are getting the solution to this integer linear programming constraint problem. So in some cases, you can really have a dramatic specialization of the generated code. Okay, so this is not a typical solution. You would probably not be this fast. And this is uniform for any number of bits, right? So you can just stream it arbitrary number of bits. Okay, and now we have some compilation techniques for constraints on data structures, although it started originally with numerical constraints. And these are constraints on sets of objects. For example, if you have a given set and you want to partition it into approximate equal partitions, you can write it like this, and we generate the code that basically computes the right sizes of the partition. In this case, you just need approximately half, and then selects a subset of one set. Okay, so this is a simple example. And for examples like this, where you have constraints on sets and for their cardinalities, we had to work on developing new decision procedures. And in some cases, these decision procedures are ahead of time of our synthesis procedure implementations, but we know that they can be used for this purpose as well. And so this is a procedure for solving multiset constraints, which is implemented just as a decision procedure so far. And for example, you can have arbitrary constraints like disjoint sum of multisets or ordinary union of multisets, and any pointwise integer arithmetic constraint. And one question that wasn't resolved before is, for example, what is the complexity of such logic? And any algorithm that we were able to find had only NXP time or worse complexity. We in fact showed that the problem is NP complete, where the hard part was that it can be solved in NP. So this is despite the fact that the sets that you generate here are exponentially large, and therefore there are doubly exponential number of the search. The search space has, in some sense, doubly exponential or infinite size, depending how you think about it. So this is just an idea of the kinds of techniques that we may need to use to solve these problems. I would like to now mention briefly a technique that we use, and that's somewhat different than these two. These two are closely related, and you can think of compilation as a way of optimizing the execution. But what happens when we develop the program itself? And here we have an approach that's based on suggesting expressions that satisfy the given typing constraints. And in the future, we plan to also satisfy additional assertions. So let's say a programmer is writing something explicitly, gives the type that they want. And then it just wants, well, how could I compute a value of this type? Okay? And so the tool then comes up with a ranked list of suggestions. Okay? You can think of this, if you're programming in some development environment, as an extension of code completion functionality, where the tool suggests you possible method names. But here you don't necessarily have method names. Moreover, the tool suggests you entire expressions. so entire pieces of program. And so the overall idea is that you collect the type constraints that you have, along with some weight constraints that you derive from the corpus of code. And then you run basically a theorem-proving algorithm, which corresponds to type inhabitation, right? So finding an expression of a given type. And then you get usually a large set of solutions, and then you rank them according to some criterion. So this is actually a semi-decidable problem in this case as well. And it's, in fact, a proof search in a particular fragment of intuitionistic logic, which corresponds to Scala's type system. And now the important thing here is that we add weights that describe which solutions are likely to be good. So we have currently a relatively simple way of saying which solution is good once you assign weights to these to the individual symbols. And we have also some classes where this is more efficiently solvable. Now these weights are based on particular heuristics that we derived, as well as how close the symbols that we are looking at are to the declaration point. But also for the API, for the library functions, we derived the frequency with which they occur in some corpus of code, and we use that as initial weights. And this, we are planning to use some machine learning techniques in the future to improve the accuracy of these mechanisms. And what is interesting is that in a number of cases, we were able to synthesize the expressions of the kind that user would want. Okay, so this is something that's difficult to quantify, but here's what we did. We took over 100 examples. In fact, this is joint work with Tihomir Guero and Ružica Piskač. And so they took a number of examples, and they examined the API usage in these examples, deleted some lines, some expressions, and then we reran the tool and said, what would you suggest? And so what happens in that case is the tool generates thousands or hundreds of expressions that have the right type, and they would compile at a given program point, and then it ranks them according to this system of weights that I just briefly described. And in these examples that I highlighted here, you really get exactly what you wanted, modular, let's say, constants. If you have a string constant, there's no way the tool would really know which string it would be. But you get the examples that correspond to what you deleted. In some other cases, you don't get that, but in, let's say, over 50% of examples, you get among the top 5 basically what you deleted. Okay, so it seems that this a relatively simple weight function mechanism can give you some interesting results. All right, and so now this sort of completes the overview and why I talked about these 3 things. I talked to them roughly in this backwards order, from bottom to top. Right, so I talk about execution mechanisms, and that's where most of the examples were. Then I talked about the compilation, which comes with some static checks, and then I talked about the development within integrated development environments, where I didn't have so much time. And so I would just like to finish with emphasizing why would it be good for something to be implicit, right? If I say implicit programming, I mean, why would that be good by itself? So it's actually not that we want programs to be implicit, it's that we want the requirements or the design of the program to be explicit. And we don't want to ask necessarily programmers to write the same thing twice. And so what I'm saying is basically if you have to choose, it would be good to have a mechanism to allow programmers to talk more about the design. If they're willing to write down both, great. Efficient program and design, especially if you know how to show that they correspond to each other. Of course, this may not be that easy. So what I'm advocating here is going more with the explicit design, and then you can sometimes leave out the program to be implicit. Okay, so I didn't go through all the results and algorithms that we use or we could use in this case, and that we developed specifically motivated by verification and synthesis problems. Some of them you could see in Ružica's public PhD thesis defense on December 6th. And so this is perhaps a good time to summarize. This is joint work with Ružica Piskač, Filip Suter, Tihomir Guero, Now, Michael Meyer was part of this work, has left since, just like Ali Sinan Köksal, who is now at Berkeley. And automata-based work is joined with Barbara Jobsman and Jad Hamza. And some relevant decision procedures are joint work with Sven Jacobs, who is a postdoc in our group. And now I would also like to thank other group members who are working on related topics that didn't make it into this talk yet. So in particular, Eva works on trustworthy numerical computation that we hope to incorporate here when you talk about, for example, floating points. Hossein is working on model checking of concurrent programs. Tien has done great work on static analysis of PHP and Scala. And Giuliano is working on distributed algorithms, and Andre on automated synthesis of algorithms for storage. And hopefully this is also closely related to what I've described. We'd also like to thank the Scala team, the Programming Methods Lab, because without Scala this would not be possible, and also without all the help that they provided. Okay, so this brings me to the conclusion right on the gong. So I described some ideas that I collectively summarize as implicit programming, and I'm happy to take any questions.
For the first KTN talk that actually ends on the gong.
I see.
Please, you can select your.
Well, yes.
I'm just curious why you prefer implicit versus explicit to other ways that people have used to describe this duality, declarative versus operational,
right,
declarative versus other ways of
you have something to additional terms. I've started to collect various programmings. And this is perhaps the most closely related to constraint logic programming. The constraint part comes from using techniques for constraint solving, in particular a finite domain constraint solving. Logic programming comes, for example, from the ability to deal with terms that range over unbounded data types. But yes, so there are others, and this is a form of declarative programming for sure. But it's a particular emphasis that I would like to place. And, so I could talk about declarative programming, but it's then not clear what I have in mind. And implicit particularly refers to, perhaps I can just draw this, right? So let's say you have okay, so this implicitly defines, let's say, y as a function of x, right?
Like rather writing the system of equations rather than writing down how to compute the solution.
Exactly. So this is what I wanted to emphasize. Although it's a more appropriate name for the first two parts than for the synthesis part.
I mean, logic programming used to be declarative until the secret of the cut rule came out.
Which seems to have happened fairly early, actually. Yeah. Yes. So, and there are, for example, functional logic programming languages like Curry that are still being developed, but they similarly have operational restrictions. So, it's part of the difficulty comes from the desire to take a somehow clean logical method for solving declarative constraints, and then give it a simple interpretation that you can tweak and that you can somehow control. And here, the idea is to more use this domain-specific approach where you have different constraints and they have their own specialized procedures. And I'm not hoping to let the programmer control, for example, how exactly integer constraint solver works, unless they really want to do it, in which case they can do it in Scala. So that you can first say, here's a constraint, enumerate all solutions of this constraint, then feed them into the next one, and so on. So you get some control, but it's sort of clearly separated. Once you say something is declarative, then more or less you leave it to the decision procedure or constraint solver to deal with this. And then you get the values, and then you can explicitly manipulate them. So yeah, so it's related to all these all these other paradigms.
Any more questions? Well, I have two. So I'll ask the two of them. You can pick one, and then maybe I'll resolve the question on the other. The first one. So these modern development processes like Agile, Scrum, and so on. Basically, what they've done is, like 10, 15 years ago, they said people are very bad at actually specifying the problem they're trying to solve. So to cope with that, we'll just kind of build a prototype, show it to them. Is this what you meant? It's like, well, actually, no, I meant this other thing. Then you kind of change. So keep going through these iterations. So I'm wondering if you thought about how you might pull that into implicit programming. I mean, how would you? Because obviously you can prototype as a programmer, but I'm wondering if there's some natural match between sort of evolving these this approach that is better or worse than the current approach.
Okay. So I was half guessing that you would ask me something like this. So I put here a loop, and I was assuming that, if I, for example, skip one of these things, then any sequence of these steps would be sort of also correspond to this picture. That's why I wrote here A or B star, which sort of subsumes all possible sequences of A and B. But so if you're asking whether, so I think this doesn't really presuppose any particular development methodology. But I think it can be helpful to be able to underspecify your programs, because you should be able to write down the important things first, and then just get some solutions, and then in response to that refine the process. So I would say that this should actually help the development approaches, these more recent development approaches and agile approaches, because it's easier to prototype things. But that's I'm not sure I have any deeper sort of
I was wondering if it is because one of the strengths is that you can now reason a lot better about what you produce. So if you actually go to a customer and say, okay, here's a prototype, and by the way, here are some properties. Did you actually think that these are the properties you want? Which today all you can do is show them the prototype, they play with it. So I was wondering if that can be factored in somehow.
Yes, I think the example that I tried to show with the red-black tree really is trying to hint at the fact that you can start from requirements, and I think that's what naturally happens, that you have some partial requirements, and then you add them up, partly in response to what you see is happening. So you realize that perhaps they were not enough or they were wrong. And in standard imperative and object-oriented programming, you don't really get to somehow conjoin programs, right? To say you have this and that, but now extra, do the same thing you were doing before, but in addition do this. So you cannot always do that if your program already does just one particular thing, right? So there's no space to constrain the possible executions. Whereas here, if you think of this as allowing a set of possible behaviors, then you can do that. So I think it may be better for collecting the requirements.
So that's actually a great segue to my second question, but are there any new questions in the meantime?
So have people tried to mix explicit with implicit programming? So when I specify my constraints and then I sort of draft how I think it can be implemented, and then maybe you can use that to have a high performance implementation.
Yeah, so I would say that our system is exactly this. It allows you to, it allows you to do that, right? We haven't done a huge case studies that show that this really helps your productivity. But I'm trying to find an example of generating the trees here. Let's say I had the example that shows testing, right? So here we defined the set, notion of a tree, a sorted tree, and then we are declaratively finding sorted trees. And then we get these trees and we can do something with them. So in some sense, once you get the value, you can obtain it in declarative way. It doesn't matter. It's just a value in your Scala program. And you can now continue to work with it in a classical way where that you perhaps are used to from before. And similarly, you compute something else, and then later on you decide to feed that into a new constraint, and so on. So you can definitely mix the constraints in this way, and including being able to iterate over the set of solutions. But I think you ask perhaps a more specific question of perhaps you can first try to write a prototype and then later on refine it to make it more efficient. And yes, you can do that. Actually, contracts are a great way to think about that. You can start by writing your functions that's annotated only with contracts, and that has only contracts and nothing else, and they will run in some sense. And later on, you can then put imperative code in that runs more efficiently than the contract itself.
So is there any, can I ask so is there any like experience from the real world? So something that's more advanced, like a company, they already have their software running. Now they're trying to prove properties, so they come up now with the constraints, and then they feed their entire code into these constraints, and they sort of try to generate code. So is there any evidence of using this in the program?
Well, this is about to appear in 2012, sort of. The system itself is very new, but we would like to use it to gain more experience with it.
But test-driven development might be something like that, right? Where you're saying, okay, here are some requirements, and then you build something kind of works, but then you're like, okay, there's this other test, let me try to fix that one.
Yes. So actually, I should say that we do have a little bit more experience in test generation, and this is something that you can use this system for. So you can actually take, so this code, it's enumerating trees, and then, as you can see here we are printing them. You can feed these trees into any program. You don't have to. It doesn't have to be Scala program, right? So you can test your C++ implementation by describing in Scala the notion of a tree and then generating trees. And this was used, for example, for finding errors in refactoring engines. So not particularly this implementation, but the related one that was done jointly with Darko Marinov, Sarfraz Khurshid, and Tihomir Gvero here, the number of students from UIUC. So this, in that related work, we generated example programs that we fed into refactoring engines, which are similar in nature to compilers. And we were able to find errors in refactoring engines and even a discrepancy in the behaviors of two different Java compilers. So basically, and you could easily argue that one of the compilers was doing something wrong. So for test, I think generating test cases is actually very good and realistic application of these techniques.
My second question was about, actually Nedelko's question brought up something interesting. He asked about the performance if you are on it.
Yeah.
So it's an interesting trade-off, right? Because you have expressibility, so also properties that you trade for performance, verifiability, and so on. And another one is maintainability. Another one is how do you evolve the code?
Right.
And that seems to, at least in practice, seems to be a very valuable property. And you mentioned earlier convolving these functions. So
conjoining, yes.
Conjoining them. So I'm wondering, is that the way you'd evolve in implicit programming? Would you actually modify your expressions, or would you just add more, or how would you go about so someone comes a year later and says, oh, I wanted to do slightly something else now, or...
Right, so if the program ends up running, or particular functionality of the program ends up running based on these constraints, as we are ultimately hoping, then you have the freedom of adding the constraints, but you also have the freedom of somehow removing some and adding some others, right? So I believe this does help you maintainability, because often you do want to think in terms of properties.
But can you treat what you put down as immutable? That's one of them. So can you just add more to it?
Yeah, okay. So, well, there are at least two ways in which you can do that. One is that you can change the code, right? And that's obvious. You can just add a new conjunct. You can also have these these constraints be in some kind of list, append to lists, and then conjoin them. And also, actually, this supports constraint programming with logic variables and constraint store, which is something that's standard mechanism in constraint logic programming. And that means that you can just have an assert that says, now assume that these symbolic constraints satisfy some constraint, and later you say, and now also assert that they satisfy some additional constraint. These constraints get accumulated at runtime. So you have both sort of static ability to change it and one fairly dynamic.
kind of feedback that might be useful for you when renewing your constraints? Like I'm monitoring your execution, not in the CPU memory whatsoever. So what is the kind of feedback that you think now might be useful from the production?
Okay, so we don't have experience from the production, right? So, but
So the production program running.
Okay, so.
So what is the feedback that I'm monitoring? I see some order methods, I see some counters, I see different things.
So you're wondering, you are having one constraint solving step, and you want to see how far you are along, or something like this. I mean, you can obviously measure all the things that you have before. You still have a software system.
Absolutely, I can measure. But I'm just saying, can you use it? Reuse it to come up with a better solution?
Yes, well, okay, so for example, these solvers inside are doing learning of constraints, and you can, for example, you could monitor the classes of constraints that you learned on the fly and use that to synthesize, to later on come up with the solution faster. So this is something that's to some extent already happening automatically, but there would be space for more things like this.
Okay, so I propose that we take the remaining questions offline so that whoever needs to leave, they can take off. But before you do, let's see if Viktor.